Good morning and welcome to the first real lecture about machine learning. I set up my new teaching suitcase. You cannot really see what's inside, but it's pretty cool. The university created that for me. It's like let me see if I can, no, you can't see that. It's two screens, it's a camera. See, it should be following me. Yes, it does. That's machine learning. Okay, let me show this to you. If I move this here. Okay. Let's see if this works. It's a wireless microphone, so the sound recording should be fine. Yeah, that all works very well. That's one of the last time we spoke about, or you told me like what you want to do as a career, and I told you also consider to become a researcher. That's one of the nice things about being a researcher and working at the university. You have a nice idea about something, and you can realize it, like this suitcase. It's just it's just nice to have. Today we talk about machine learning. I give you a broad overview, and we will learn about the first algorithm in machine learning, KNN, but later about that. So today we will do the full 4 hours. I will show you 2 or 3 more examples how great machine learning is, what it can do, things that I did for my work. This is a simple example. I hope the sound will work. Just listen. Okay, the internet seems to be extremely slow. I hope that at least the video of me is all right. All right, it doesn't seem to work. I don't know why. Whatever. Listen to this at home. And you've probably tried many of these things. You can use machine learning to create images like this, tell them which style to use, tell them what exactly to paint. I showed you some examples last time already with the baseball player. It's very impressive, so I assume this also won't work with the audio. This is already relatively old in terms of machine learning. I think it's 3 or 4 years old. It's a conversation. It's from Google, where Google programmed a bot that is making a reservation for a hotel. And I would believe that you cannot distinguish who's the human. So actually the person in the restaurant taking the phone call is the human, and then the person making the call is the robot, but you can't tell the difference. It's so good, it's so realistic. Yeah, let me see. So it's a pity that let me try again, because this is really a good video. So let's see how does the audio works here. Yeah, I have no idea. Okay, so also please listen to this at home. But just to show you, it's like live translation. So the guy, this guy is talking, and then in real time, machine learning is transforming his speech and his face into the face of Obama. And again, this is a few years old, and if you look very carefully, you may realize, okay, it looks a bit weird. Obama looks a little bit weird, but on first glance, you wouldn't recognize it's machine learning. There's many more examples. I put them to the end of the slide deck. Before we talk about machine learning, one question. So we said we start 8:15 and now it's already 8:25 almost, and many of you are just arriving. If we schedule this to 8:30, yeah? But then you will be on time or you will just arrive 8:40? Okay. Okay, then we will do this. Okay, good. Then we will do this 8:30 in the future. So before we talk about machine learning, let's talk about how you solve problems normally with a computer or as a human without machine learning. How do you do that? You're a computer scientist, most of you are probably in the 3rd semester, so you had already 1 year of lectures. You have some experience with computers. You have learned already to solve some problems, probably something like this. Sorting, let's start with this. Which sorting algorithms do you know? Bubble sort, yes. What else? Yeah. Deep sort, something else? At least you know there is quite a few sorting algorithms, right? What makes them, well, the name says it already, it's an algorithm. So what does that mean if you would explain that to your grandmother? What is bubble sort doing? Not exactly what it's doing, but at a high level. What is an algorithm to solve a computational problem normally? Yeah. Yeah, exactly. It's like a recipe, meaning it's a set of rules. So it says it's like a recipe, very good comparison. First step, second step, third step. Look at the first number. Look at the second number. Which one is larger? If first number is larger or smaller, move it 1 position up. One step, one step, one step, one step. That's an algorithm, typically. That's what we have learned so far. And this works well for many things. Let's assume we wanted to extract a title from a document. What would be a very simple algorithm? Check the font size. Yes. What exactly? The largest font size, probably. Would that work perfectly? No. But that's no problem. Machine learning also doesn't work perfectly. So we don't need to have the goal of a perfect solution, neither for rules nor for algorithms, for rules, for machine learning. Okay, sorting, extracting titles from documents, that all works quite well with standard problem-solving computer science. But what about autonomous driving? Well, let's start here, spam detection. How about that? You're too young to remember that, but in the beginning of the computer age, spam detection was being tried to be solved by rules. You had blacklists, and if any of these words occurred in an email, it was assumed it's spam. And the spammer, of course, adapted very quickly. They replaced maybe some letters, an O with a 0. Like this was the original word, and then they replaced it like this. And then the spam filter didn't recognize it. And then the email providers adapted the blacklist, changed the blacklist, and added the second, like this word to it, and so on. It was a cat and mouse game. Didn't work very well, was very labor intensive. Autonomous driving and face recognition, it's impossible to come up with a simple or with some rules that can make autonomous driving. Same about face recognition. You cannot make rules that say, okay, if this pixel is like this and this pixel like this, then it's this person. So the standard approach to problem solving in computer science is algorithms, some rules, heuristics, or brute force. Brute force means just you try out everything if you want to break a password, for instance. That's an illustration. That's how you come up with an algorithm, and that's also how and why there's so many solutions to sorting, where you have bubble sort, merge sort, and so on. You study the problem, so you know, okay, there's an unsorted list. You want to sort it. You come up with some idea and write your algorithm. You look how good it works, good in terms of how fast it is or how effective, how accurate. If it's good enough, you launch it. If it's not good enough, you analyze the errors and continue again, like this. So in the beginning, I don't know which sorting algorithm was first, but someone came up with, let's say, bubble sort. It worked reasonably well, but it had a relatively high complexity. And then someone else had a better idea and came up with a different algorithm that was faster or required less memory. A very still nowadays good solution to problem solving is human labor. Many problems still cannot be solved by computers. You need human labor. What's a simple example? What is still very often, like it's attempted to be solved by computers, but it's not working so well? Any ideas? I'm sure there's many examples. But one example are captchas. You know this from logging into some web services, and then you have to type in or choose or drag the images in the right way, because computers cannot yet do that. It's spam protection. But if you are a spammer and you want to automatically or semi-automatically use some service, what do? You hire cheap labor. There's websites like this. They offer you to solve captchas for you. So you program something. When your program sees the captcha is being sent to some human laborer. That person gets, I don't know, 1 cent or whatever to solve the captcha and sends back the code to you. Maybe you know Amazon Mechanical Turk. So it's from Amazon. So it's big business behind that. Amazon Mechanical Turk allows you as a researcher, as a company, to upload some task, almost any task, to rate images, to write some text, to compare images, whatever. And then there's humans who are doing these tasks. Also, machine learning relies heavily on cheap human labor. As you will learn in this lecture, machine learning requires often labeled data. So machine learning algorithms need to know what is the right answer. And it's often not just there, the right answer. You need someone, a human, to tell the machine, this is the right answer. This is what I want you to output. And OpenAI required lots of this labeled data, and they use cheap human labor to do that. Okay. So now let's talk about the machine learning approach to solve problems. And in this, so there's 2 types of machine learning. You see that on the next slide. There's supervised machine learning, supervised and unsupervised. Sorry. In this lecture series, we focus on the supervised learning. And that normally means you know the right answer, you show some input to the machine learning algorithm, and you show the desired output. And then the machine learning algorithm will automatically learn what to do to transform the input that you are giving to the desired output. And typically, at least in the beginner machine learning lectures, we talk about input as instances, and that's typically a row in a table. So when you work in the lab sessions here with machine learning, typically you just have some tables. We later call it a matrix, but that's basically the same. So just every row in the table is one instance, meaning describing one thing, one input. You will see examples later. And then there's 2 types of labels, or also called targets. That is what you want to have as an output. 2 types. First type is a number. So you want to output a number, oh, sorry, here number, or a class. A class would mean maybe a cat or dog. You want to make a classification. You want to know, is an image a cat showing a cat or a dog? Is a customer satisfied or dissatisfied? Yeah, something like this are classes. And then you choose a metric to measure the performance. If you predict a number, then typically you want to measure the error. So you know the right answer. You will have the output prediction from the machine learning algorithm. And ideally, of course, it should be the same. To measure the performance, you just measure the difference. Or accuracy, to measure the performance of classification. So how many images were correctly classified as a cat? So maybe you remember last time I told you, wait, let's wait for those two because it's important for them. Maybe remember last time I told you if you log in to WebEx with your university account, you are not being sent to the lobby. You can directly join this lecture. Okay. It's important to keep in mind that there's not the one machine learning algorithm, the one machine learning method. There's many, many different algorithms for machine learning, but they all have in common that they get some input, and then this algorithm somehow is learning how to transform the input to the output. And there's many different ways of doing that. So the process is a bit different. You still, of course, study the problem to understand what you want to do. But then you are not writing a rule. You are not writing your own machine learning algorithm. You are taking an existing machine learning algorithm and train it. When I say you train it, it means you make it learn how your input should be transformed to the output. And the training is based on the data that you have. And if something changes later, you are not changing the rule. So thinking of the spam example, you are not changing the rule, okay, now if a 0 occurs in the word, also classify it as spam. The algorithm remains the same. You just put in the new data and it will learn it again. And the rest remains the same. You evaluate the solution. If it's good, you use it. If it's not good, you analyze the errors and continue here. But when you find errors here, again, you don't change the algorithm. You would change, I mean, maybe you use a completely different algorithm, or you would just change something about the data. Yeah. We talk about this later. You can also tune the algorithm, but that doesn't mean changing the code, like the algorithm itself. It means changing some hyperparameter. And every one of you knows these examples. If you are, I mean, who here is using Gmail? Can you raise your hand? Yeah, many. And most email programs have that. I'm not sure if you're using this feature, but it makes a lot of sense. You can classify emails as spam or not spam. So that helps Google to train their machine learning algorithms to improve spam detection. Yeah, that's what I just said. Now, it's early in the morning, so we do an example to wake you up, a classification example. And forget about machine learning for now. Just look at this example and think about, will Johnny like this pie? So you know already Johnny likes these pies. And you know already Johnny does not like these pies. Now you must make a guess based on what you know. Will Johnny like or dislike this? Think about that for 2 minutes. Talk with your neighbor if you want. He will like it. Why? Okay, one moment. I prepared like this, so all of you can vote after that we discuss. And I can tell you already, there's no right or wrong here. Yeah. So if you could please take your phones or tablets, go to menti.com, type in this number, and tell me what you think. Okay, the vast majority of things he will like. Let's go back. Well, no. So last year's results were very similar. Why do you think he will like it? How do you define similarity? What? Based on shape? So because it's round? Yeah. So you looked at the shape, the color of the inside, and you then believe that this is more similar to the other cakes that Johnny likes. Yeah. So let's make this a bit more analytical. It's obviously the right way to look at the features and then look for similarities. What features do we have here of these pies? You said already the shape, the color, something else, size, right? Like this here appears smaller than the others. Size, yeah. Proportions. Yeah, it's pretty good already. So actually, that's a good point. Proportion, this is not included here, but then again, there's no right or wrong. So what I have here is the shape. It can be a circle, a square, or a triangle. The crust size, thin or thick. The color, filling size, thin or thick. But basically, when you say proportion, that's like the ratio of filling size and crust size. Yeah, that could also be a meaningful feature. And then we have the target or the label, also called the dependent variable. And that's something you need to get used to in machine learning. There's very often specific terms, like sometimes different terms for the same thing. So target, label, and dependent variable, it's all the same. Right, those are the features, and then you try in your brain to come up with some rules what to do. So one way, what you could do is this. So that sounds pretty much like what you did actually. If the shape is a circle and the filling shade is dark, then Johnny will like the cake. Otherwise, he will not like the cake. Now, once you have this rule, let's look how well it works for the existing cakes where you know the right answer. So with this rule, you classify 4 out of 6 likes correctly. Namely, this one, it's a circle and it's a dark inside. So you predict he will like it, and he actually does like it. Same here. This one you would incorrectly classify because it's not a circle and the filling shade is not dark. So you would classify it as dislike, but actually, as you know, based on the given data, Johnny does like this cake. Same for this. So in total, and you would correctly classify all of these as not like. So in total, you would have classified 10 out of 12 of the cakes as correctly. That's an accuracy of 83%. That's pretty good. Now, as I said before, you don't want perfection in machine learning. And of course, you would like to have it, but you normally never achieve it. Now, what would you do if you had to do this for thousands of users? You have a system, a recommender system or whatsoever, where you want to recommend cakes. Here for this single user, you could do it in 1 minute. You came up with a pretty well working rule. But every user has different tastes. You cannot sit down and do this for 10,000 users. So you must come up with an automatic solution, and that is machine learning. That is just then another way of representing this in a table. And now the question is, by the way, most of these images are created with machine learning. Also pretty cool, I think, quite nice. So now think of an algorithm that can come up with a rule automatically. Do you have any idea, or have you learned of any algorithm already that can do that? You have these labeled data, and similar to a sorting algorithm, you must now come up with an algorithm that eventually gives you a rule like this. Yeah? Yeah.
Each one within kind of scope.
Okay.
And some of them test as a visual problem.
Yeah. It needs to be more specific. You need to have like really like very simple steps that the computer can follow. So, and I'm doing this in this lecture to make you, I mean, we go through this quite quickly, but this is what you need later when you have a job. Yeah, you will be faced with problems like this, much more complex problems, and you're computer scientists, and you need to develop novel algorithms. So you were first. But you can also talk in German.
Welche Punkte meisten quasi vorkommen. Und dann dass man da vielleicht dann erkennen kann, okay, die meisten Leute mögen den Kuchen, der jetzt diese Form hat, vielleicht diese Füllung hat.
But that would give you, the student said, maybe you can look at the points that occur most often, and then you can see what most people like or what works for most people. But you want an individual solution for every single person. You want the best rule for you, the best rule for you, the best rule for you. Yeah. Ja.
Man könnte es auch eben als Graphen darstellen, dann zum Beispiel schon eintragen, welche eben gemocht werden und welche nicht gemocht werden und sich dann eben die nächsten Nachtwanderungen anschauen.
Okay. You could represent it as a graph and then maybe look at the nearest neighbors, possibly. I'm not sure about that, but I will show you the probably most simple solution. It's called hill climbing. It's a generic approach to find a solution. In hill climbing, it's not really a machine learning algorithm, but it shows you the idea. Or it is used in machine learning. So you just start with a random rule, the most simple rule you can imagine. For instance, what happens if you just say, if the shape equals a circle, he will like it? Well, in that case, you would do quite well already. This would be correctly classified, correctly classified, correctly and correctly classified. This and this would not be correctly classified, actually the same as before. And here these two would be misclassified. So you start with your most simple single iteration. After that, you look at all possible combinations. So you keep this rule, shape equals circle, shape equals circle, shape equals circle. And you take a second, you take all the other possible combinations. So the fill shape is dark, the fill size is thick, the crust size is thick. Yeah, all possible combinations here. And you look, which one is best now? And actually, this one would be best. That's what we had before. That gives us this. That's exactly the rule we had before, that you came up in your head with, and I showed on the slides. So now you only have 2 out of 12 misclassifications. Here you had 4. So out of all these possibilities, this one is best. So you continue with this. And you add a next variable, all possible combinations. So shape equals a triangle, crust shade is dark, fill size is thin. And then you will find that this one is improving. So you only have 1 error. And you could continue this until you don't improve. Now, this is a greedy algorithm. It's not guaranteed to give you the best possible solution. It could be that maybe if you are not using this, but maybe this and some other combination, it gives you an even better solution. Still, this simple algorithm will give you the perfect rule for, not the perfect rule, will give you a good rule for every individual user. So let's see. Yeah, so this finds only local optima, meaning not the global, not the universal global best solution. And of course, it's very expensive in terms of computational power. This works fine for a few dozens of features. If you think of nowadays machine learning applications where you have millions of features, this doesn't work. That's exponential. It's just far too expensive. Let's look at some other example. Second. Let me ask you, your bachelor students, master students, once you graduate in a few years from now, how much will you earn? What do you hope? What do you think? Be realistic. So that's quite a difference. Some of you expect a rather low salary. Few of you expect quite a high salary. It's actually quite a normal distribution here. Most are in the middle. I mean, okay, obviously you study different things, so maybe some of you expect different outcomes, but how did you come up with these estimates? Sorry? By prior knowledge of the job market. So I don't know, you looked at some newspapers or whatever, and they tell you, or you ask some friends, or how did you get up with the prior knowledge? Glassstone, so some websites where they tell you, in this job, on average, you earn this. Okay, any other ways you came up with these estimates? Oh. Yeah, like your friends. So maybe then you also know, okay, you are smarter than your friends, so maybe you will earn a little bit more than your friends, or less, something like this. Yeah. You have compared yourself with peers. You have looked at some global sources. Now, what do you think if this data is given in a table again? So you have here student IDs, the time they spent to study per week. It's probably unrealistically high. And then the average marks they received and the salary they received after graduation. If you had to make a guess for this student who works 15 hours a week, has an average marks of 2.0, what would this student earn? I think we can skip the Mentimeter, but this is a real typical machine learning problem. You have labeled data. So this is your input from row ID, student ID, study time, average marks. The salary is the label, the target that you want to predict. And then for some new instance, a new student, you have the same input, but you want to make this prediction. About this scenario, we will talk a lot in the next 12 weeks. That's a regression problem. You want to predict a number, the salary, for this student. So, could we try hill climbing here? Yeah? No? Yeah. Why not? Yeah. Yeah, correct. It would not be, I mean, if you would transform the data, maybe somehow you could apply it, but not easily. So in general, first thing, what is always good to do if you have data is visualize the data to come up. So we are talking now again about brains. Imagine you're in a company, you have this data, you need an algorithm to come up with a solution. It's your task to do that. First thing is visualize the data. So let's look at, we ignore the row ID and the student ID. We look at study time, average marks, and the salary. And we plot that. It's three-dimensional. It's a little bit difficult to visualize. So the larger the dots, the smaller y is, I guess. So let's just look at one example. The first student studies 72 hours, so that's here. He has an average mark of 1. Wait. Yeah, exactly. So it's a small y, so it's a large dot. Yeah, so that's this one. And he has an average salary of 58,000, so roughly going here, yeah, roughly 58,000. You cannot really see too much. To make it more simple, let's remove one dimension. Wait a second. Oh, no. No, sorry. So if we now have our unknown student, this one, we know the student will be here, 15 hours study time, average marks of 2.0, here 2.0. So somewhere here, this student, this unknown instance would be. The question is where? And we can see this as a mathematical function. We know that z depends on x and y. So f, the function f of x and y equals z. We know that if the study time is 72 and the average mark is 1.0, the output z is 58,000. We know that if study time is 63 and 3.7, output is this. So the question is, what's the output of this? So now let's make it a bit more simple. So what's the function, the output of this student if the average marks? So we removed study time to make it more simple. We only look at the average marks. What's the output here. And I think now you can already, how would you do it now? If you had to make a guess. We know the student is somewhere, the average marks are here. So the salary will be somewhere in this area. Yeah. So he would, the student said he would look at the nearest, so you probably would say somewhere here. Yeah, 50 and 6. So remember, we have a function here. We don't know how the function exactly looks like. Yeah, so it's somewhere here. We have a function that we don't know how it looks like. It could look like this. Could also look like this. Again, we are not expecting a perfect solution. I mean, this one would be a perfect solution for the existing data, but we can always, whatever function you have in machine learning, you can expect some noise, and you want always a simple function. It's easier to train and to design. So it could look like this. It could also look like this, but it could also look like this. Any of this. So there's an indefinite possible space of functions. We need to find some function. And when I say how to find the best function, f optimum, what does that possibly mean? Just one. So once we have this function, that is, then we can easily calculate the salary for the student. So if we believe that this function here is best, then we can calculate the salary for the student. It would be maybe 65,000. If we believe this function is best, then we can calculate the salary and would have output, I don't know, 48,000. Someone raised their hand about what's the best function? Yeah. The one from the top? Why? Because it's closer to all the points. So you believe. Oh, but anyway, that's the right direction to say it's closer to all the points. So it's modeling the existing points better than the others. Now, we will learn about this in the next lecture, so like in today's second part in more detail. For now, remember, regression means to predict a real number, like a salary, and there's not the one algorithm to do regression. You will later learn about linear regression. That's exactly what I showed to you, to find basically a line, a linear function that is modeling your data, but there's many other regression algorithms more. Before we come to these algorithms, step back and talk about machine learning a bit more. But this is, just coming back here, this is the core of this lecture series, how to find functions like this. And there will be a few alternative algorithms where you don't find a function, but you have some other approach. But still, in the end, it always comes down to this. Look at your existing data, come up with some rule that you can apply to make a prediction for the new data. Just have a look of these definitions. And tell me which one you like most.
because we're talking about experience, so that the computer needs to learn from data, which is another parts. Also, that it's always like focused and oriented on a specific task to solve.
Okay, I agree with you. I also like the third one most, but this is subjective. If you like another one, that is fine as well. But still, the third one is just very specific in terms of, in my opinion, it has all the important components. You have, I mean, it's using a bit weird wording, but like the experience E is just the data that you have, the historical past data, it's your experience. And based on that, you can learn a label, the target, which they call a task here. And it's always important to measure the performance. In many areas, it's very difficult to measure performance, especially in recent developments with machine learning. How do you measure if ChatGPT is better than Gemini, for instance, in writing texts at a large scale? Of course, you can just look at it at one or two examples and say, well, I like ChatGPT more, and then someone else says, oh, but I like the output of Gemini more. So how do you evaluate that at a large scale? It's not easy, much more difficult than evaluating the examples we have here, like predicting the salary. If you have a large enough database with existing salaries, you can do that in minutes. Anyway. Yeah, so that's what I just said. Your experience is a number of data points meaning instances like students, or if you want to predict house prices, then these are houses. A number of features like the study time, and then your target and label. And here's the important part. Based on the data, you are training a machine learning model to output this. And yeah, I'm sorry, all these different words. So you must learn that. It's like if you learn a new language. Instance and data point, attribute, feature, or independent variable, all the same, target, label, and dependent variable. I will also use these terms interchangeably. And then once you have built your machine learning model, you want to apply and test it on new data, or more precisely, but we will learn about that in a different lecture. You are training your model on this data, testing it here, and then apply the best models in the real world on your production data in a company. There's a number of different types of machine learning. I mentioned this already, and so far we talked about supervised learning a lot. That's this. We don't need to repeat this. But then there's unsupervised learning. The difference between supervised and unsupervised learning is that at a low level, in unsupervised learning, you do not have labels. So you still have your instances, your students, and the features, but you don't have the right answer given. So that also means the goal of unsupervised learning is typically not to make a prediction, this will be the salary, or the customer will like this product but not this product. The application area is different. You can do clustering, for instance, where you will group your customers or your students or whatever into different groups. And then maybe you use these clusters or groups to send out targeted advertisement, make some special offers, or group them into different lectures. I don't know, something like this. When it comes to image generation, that is also often unsupervised learning because there's not the one right answer. If you want to merge this and this together, there's millions of good outputs. Or if you create a complete fake image. Yeah, also this video that I wanted to show you, have a look at that when you are at home. All supervised learning. There's semi-supervised learning. So maybe in the beginning it's unsupervised. Someone, like some software tool, is showing you images. And then you are saying, oh, this is my friend X. This is my parents. This is my friend A. And after that, the machine learning program knows this, and then it's supervised learning. What is really interesting, what is really interesting is reinforcement learning. We will not talk about this a lot in this lecture. I just want you to be aware of it. Reinforcement learning works with agents who are trying different tasks and then getting a reward if they do it right. These agents, so an agent is like a computer program, like an AI tool that is trying out different things. They normally don't know anything in the beginning, so you are not telling them the rules of a game, for instance. It's like a baby. Yeah? You take a baby, you put it into some play area, and the baby's just trying out things. And if something works, let's say the baby has a ball, and the baby hits the ball and sees, oh, the ball is rolling, then the brain learns, the ball can roll. And it's very similar in a computer game. The best solution is just to show this to you. We don't need audio for this. Oh, and we don't need advertisement. Let's try that. This I really want to show to you. Tja, I don't know why this is not working. Okay, I really can only recommend to you look at this. It's really impressive. And reinforcement learning, for many years in the past, the research community thought, okay, it's fine, it's all right, but not really exciting. But maybe you've heard of DeepSeek, like a competitor of ChatGPT from China. Half a year ago or a few months ago, they used reinforcement learning to improve large language models, so the foundation of ChatGPT, significantly. Basically, you can use this to have two AI agents playing with each other. And when I say play with each other, it can mean anything. It can mean talk to each other. It can mean playing some computer games, and they will improve a lot. Machine learning is amazing, like I told you. It's very good for many things, but not for all things. It's good for things that require too many rules for a human to write, like autonomous driving. A human cannot write enough rules. The problem is too complex. Or where the environment is changing a lot, like spammers who always adapt to your system. You don't want to update your rules. It's much easier to update your data. And problems where you have labeled data. So if you are in a company and you have lots of data where you know the right solution, that's perfect for supervised learning. Machine learning is not good for many important computational problems like random number generation, to encrypt or decrypt data. Even very simple operations like just to copy data or to move data or rename data or to like all those file operations, to store data, to remember data, all this is not yet at least a suitable task for machine learning. Or if you want to follow exact procedures, you cannot be 100% sure that machine learning is going to do that. If you have tried that with ChatGPT, for instance, and you tell ChatGPT, please do this and this and this, like maybe write about this, write about that, or then look up this website and do this. It's pretty good, but you cannot 100% be sure that it's going to do that. With an algorithm, like a standard algorithm, you can be 100% sure your computer is doing step by step as the algorithm tells it to do. Yeah, so that's one of the challenges with machine learning. It's not deterministic. You don't know exactly why sometimes at least, you don't know why the output is as it is. There's legal implications based on this, like especially for autonomous driving. If you have a self-driving car and there's an accident, whose fault is it? Is it the fault of the driver? Is it the fault of the machine learning algorithm? If you don't exactly know how the machine algorithm came to the conclusion to stop the car or to drive to the right or to the left, how can you determine how serious the fault was? Testing machine learning is really annoying. I mean, you're still, so who of you has done something like unit testing, like, some standard testing? Yeah, just a few of you. I mean, to test normal software is very simple. Like for a sorting algorithm, you can write a simple test where you just then in the end compare, has the list been sorted? And you can debug the process. You go step by step by step. I mean, a sorting algorithm is basically like 2 or 3 steps for each sorting progress. Yeah, take this number, compare them. If make the comparison is larger, smaller. If yes, put to this part of the list. You can debug that easily. You cannot do that with machine learning. It's really painful. Sometimes the experience, you have a good idea, you try out something new, you change your data, and then you must train your algorithm again. It can take minutes, hours, days, sometimes weeks. You're probably aware that tools like ChatGPT, they are being updated every few months because training them takes a few weeks or months, and it costs millions of euros. So if you do a mistake then, and you have to do it all over again, you have wasted a lot of time. If you do a bachelor thesis and you want to try out different machine learning models, but it takes 1 day or even a week, you have a problem, right? I mean, you only have 4 months in total. You cannot afford to wait 1 week and do nothing. Yeah, this is just some overviews again. So here we will always look at simple examples, but always keep in mind it can be much more complex. So the input to machine learning can be anything: images, videos, audio, text, tabular data, whatever. If it's a number of this, it's called multimodal. That's also a recent trend with ChatGPT, that you have multimodal inputs or outputs, and then the outputs here. Yeah. Look at that maybe at home. Yeah, this is important. Text. If you want to represent text in a table, if you want to have a document represented and being used for machine learning, the most simple example would be this. Each term in a document is 1 column. Each document is a row. And then you would just count how often the words occur in a document. So for instance, here, the term and occurs 2 times. So for this document, you would count a 2 for the word and. What's the disadvantage of this if you represent documents like this in a table? The table can be very large. Yeah, that's right. Something else, maybe more. Yeah. Yeah, you're losing the sequence. You cannot, once you store the data like that, you cannot reconstruct the documents. And of course, the sequence can be very important and meaningful. So this here is called a bag of words. It's like you have a bag, you put in all the words, shake it. It's still very important, meaningful. You can do a lot of this, a lot with this, but you're losing also a lot of information. Images, we will talk maybe in the very last lecture again when we talk about convolutional neural networks. How about how to classify images? You have grayscale images, you have color images. Color images typically are represented as RGB, so red, green, blue. So each pixel has 3 dimensions, which makes it also a bit more complex for machine learning. Good. I showed you this example already, basically hours spent for coursework, and well, here it's not the salary, but the marks. If you build a model like this, if it's linear or some other way, it's called a model that is modeling your data. There's other approaches to machine learning. We learn about that later, like K nearest neighbor, which is called instance or memory based. You do not have a training phase to build this model. You will probably understand that after this lecture. So look at this slide again in 1 or 2 weeks. And then parametric versus non-parametric models. You will learn in this lecture series about linear regression, where you want to build a function. And a function means you have parameters that you need to find. There's also non-parametric machine learning, like a decision tree. Again, you will learn about that later. Okay, I think we can skip through this. Also this, if you're interested just in a big list of different algorithms, look at this. Or if you one day need some guidance when to choose which algorithm, this can help you. Yeah, you start here, then you look at, do you want to predict a label, yes or no, and so on. Then you will end up with some different algorithms that you can use. Yeah, here the same. Good. That was the first part of this lecture. I suggest first, if you have questions, ask questions, and then we have a short break. Any questions? 10 minutes break? Question? This one or? Yeah, it's often a mix, but yeah. 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 If you talk about tools like ChatGPT, it's not just a single algorithm. It's like a big pipeline of different things they do. They have primarily a large language model, which looks at huge amounts of text information, but they do a fine-tuning based with human labor. So as far as I know, the human labor is about fine-tuning the output of ChatGPT, like saying, okay, that's a good answer, that's not a good answer. Yeah, yes. Good. 10 minutes break, and then we talk about the first real machine learning algorithm in detail.